Oh, interesting. Maybe I'm not. Maybe I've been unmanned.
Huh. Okay, that's great. Congratulations.
Yeah, thank you. Because I'm currently live streaming this out my window.
Oh, where's this?
No, it's just pointing out though.
Oh, where's the camera? This thing here? Oh,
Yeah.
it's going up and out. I see. Cool. Hey, congratulations. Unbanned.
I can always go back if I really want to.
The only other thing is presentation bonus.
The glasses, like undergrad, I'd go pay to take undergrad classes to catch up. Or she's like over the whole program. Basically, like, I don't know. She was very like, she had been on me, trying to get me to go get me to the analytics program. And then that was my PhD program, which I was like, I was expecting that, but like, I'm trying. And then it didn't happen. But now, but in December, that's fine. She said I was.
Oh, yeah.
So I just felt like I was being like,
Check to make sure it's in presentation.
And like this is. The other question is,
These are plug and wall.
I mean, the machine is powered on.
I need to make sure. Hi. Hello. Hello. Thanks for coming. Pass around the toy. Hey Sam, did you get the pineapple one?
No,
I did. It was just the cords and the certificate. Yes.
I received it all.
I figured you did. First disseminator.
If I did, yes.
Hope the job's going well. I hope the job's going well. You started a new job right then? I hope that's going well.
Yeah, it's, so they, I called up somebody to, one of the tutors in that sports center.
PCL.
Oh, or unless this is
And they just called me in advance and said, can you start tomorrow effectively? I guess I have to. But yes. It's a very low-key, pleasant job. With math is all I ever want to do.
Whatever change we did, it works out.
Alright, go ahead and. Just give it a second. Yeah, I promise it will come up in just a minute. Or actually, no, I like published earlier, so actually I bet it's.
Is it publishing now? So it's probably already.
We'll check it. Let's go and get it started, and then I'll check on the laptop, and we'll troubleshoot if we need to. Or here, I can check very quick. I don't know if it's recording. We'll get it started. Maybe it'll pop up, maybe it won't. We won't worry about it either way.
Oh, yeah, what's your favorite kind of billiards?
If it doesn't pop,
Not yet. Not yet.
we'll get it started. We'll just record it. I'll post it later. Okay. Are you ready, Diana? All right. Good afternoon. Sorry, we've had a few technical difficulties here in our last colloquium. But this is our last colloquium for the semester. But we'll start back. I think we already have, I think it's August 23rd, 2019, so you can go ahead and put that on your calendars. But today, we're very happy to have Dr. Diana Davis, currently a visiting assistant professor at Swarthmore College. Diana did her Ph.D. at Brown. After Brown, she spent time at Williams and Northwestern, and before coming to Swarthmore, and she's at Swarthmore now. Diana has given talks all over the place, including recently a talk at the Fields Symposium for Miriam Mirzakhani, who won was the first woman to win the Fields Medal in 2014. It's a tradition that the person who wins the Fields Medal gives kind of a number of talks at the Fields Institute, but unfortunately she passed away before she was able to do that. And so actually a number of people were invited to give different talks, including Diana, which is quite an honor. And so we're very happy to have her here today. And so with that, I'll stop talking and let her start talking.
All right, well, thanks very much. It's wonderful to be here. I actually came through Boone 2 years ago on a road trip, and it's beautiful, but now I'm happy to meet all of you. I don't think I actually talked to anyone in Boone the last time, but here I am. This is my first time giving a math talk in North Carolina, and this is the 17th state in which I've given a talk. So I'm, trying to increase my numbers in all the ways. Okay, so I'm going to tell you today about 3 flavors of billiards. If you think about billiards, you usually think about inner billiards, which is like a ball bouncing around inside a shape. But there are these other interesting kind of billiards, outer billiards and tiling billiards, that are really neat, and I'd like to tell you about them too. And so, I'll talk about each of them, and then at the end of our discussion of each one, I made a chart behind here, and we'll sort of record our progress and some things we learned from them. And the idea behind that will be that they have all kinds of different rich properties, and so we'll see that the chart has all sorts of different things on it. So that's the goal. There will also be a magic trick, and you all are passing around this cool object, which is related to the picture on the screen. So when we get there, that's in tiling billiards, so you can pass it around till then. Okay, so the first one is inner billiards. This is what you think of when you think of billiards. You think of like going to the pool hall or something like that. So it's a particle bouncing around inside a polygon in this case. So the angle of incidence equals the angle of reflection. So in the square or the circle, but let's say the square is the simplest kind of billiard table. So here's some periodic paths. That's what I like the most. So this one just goes back and forth with period 2. This one goes in a square of period 4. And this one over here, I guess you can see it bounces around with period 6. Okay, those are pretty simple. So I also study the pentagon. I'm like the world expert in pentagon billiards. So you might ask, all right, I'll turn this down. So I made these pictures. Nobody had studied the periodic paths on the pentagon before I did. And look how beautiful they are. So beautiful. I mean, when you compare to like the square, I mean, the pentagon is really where it's at. So I made these with my collaborator, Samuel Ladiapa, and there we are. So there's Samuel. So as you can see, we're in his office in Paris, outside of Paris, working on this project on the board. So there we are. So here's a tool that people use to understand billiards, which is called unfolding. So when you look at this path, this is a billiard path that bounces when it hits the edges. But to me, this looks kind of ugly, because look, it's going 4 different directions. That's a lot of different directions. I'd really rather it would go in only one direction. So what you can do is when it hits this first edge, you can unfold it up so that it goes straight. And then when it hits this right edge, you could unfold it to the right so that it goes straight. And then you can keep doing this, so we would unfold it at the top. And so then we get this line on a piece of graph paper. And so I hope you can see that a billiard on a square is equivalent, really, to a line on a piece of graph paper, which is much easier to understand. Yeah. So you might ask, like, for which directions is the thing periodic? So suppose you want your billiard path to be periodic, you're going to hit it with your pool cue, and you want to know which direction should I hit it so that my path is periodic. Well, it turns out that the slope of the trajectory, that happens when the slope of the trajectory is rational. So rational slopes give you periodic trajectories, periodic trajectories come from rational slopes. And the way you can see it is by using this picture, but this unfolding picture. So suppose the slope is rational, then there'll be corresponding places where the same thing happens. So this is a slope of 2, it's quite simple. So this distance is the same as this distance. So if you folded this up into a billiard table, your ball would be back in the same place, going the same direction, so it would be periodic. On the other hand, suppose you had an irrational slope, well then you'd never get back to the corresponding place, and so it would never repeat. And so that tells you that rational slopes are what you want. So, there you have it. Okay, so here we have shown that a rational slope, P over Q, well, gives you a periodic trajectory, and an irrational slope is not periodic. So let me go into that a bit more. So suppose your slope is P over Q. So the rise is P and the run is Q. Well, what that means in the square is that it's going to hit the top P times, that's the rise, and it's going to hit the side Q times, the run. Kind of makes sense. And because everything is symmetric, it'll hit the bottom and the right the same. So it's going to hit P times up here and P times down there, Q times over here and Q times over there. So the period is going to be 2 times P plus Q. So the more complicated your irrational slope, the higher the period. Okay, on the other hand, if you hit it at an irrational slope, it will not be periodic, and in fact it will fill up the table densely. So eventually it will look like this. And here's something that's kind of amazing. Work on billiards has focused on this case. Like, people like to study irrational behavior. They ask whether things are equidistributed, meaning that it's basically just all solid color. Non-equidistributed would be like it spends more time on the left side than it does on the right side or something like that. This is what people study. Or is it ergodic? But in some, I like pictures, and so I look at it and I say, really? Like, that's what you're studying? So that's why I have chosen to study periodic things, because you can draw pictures of them and they're often very beautiful. Okay, so I have a question for you. Which is more likely if you hit your ball? Is it more likely to be periodic or dense?
Dense.
Dense, yeah, right. Yeah, it's dense with probability 1, because a randomly chosen number is irrational. So, you know, this may not have occurred to you that if you go down and shoot pool, you might think, oh, it's likely to come back to you or make some sort of a polygon and come back, but no, it might come back within some epsilon, but it will for sure be irrational slope. So that's interesting. Okay, so then what I wanted to do was record what we have decided so far. You got this. So let's look at the different behaviors that can occur in billiards. So here are some interesting behaviors that can occur. And let's fill this in for inner billiards. So can you get periodic behavior? Yep, you can get them. Yes, for rational slopes. How about dense behavior? Yes, you can, oh, yep, same color. Yes, for irrational slopes. How about escaping trajectories? This is the one that doesn't make sense. So of these 12 boxes, this one doesn't make any sense, so sorry about that. Okay, and then here's something that you might care about for a dynamical system. Is it stable under small perturbations? So what I mean is, suppose you're like, I'm going to put my ball right here, and I'm going to hit in this direction. And then suppose you're off by a little bit. Does it tend to do this basically the same thing, or tend to do something different? That's what it would mean, stable under small perturbations. What do you think, stable or unstable? Yeah, unstable. Yeah, exactly. Because a small change takes you from a rational number to an irrational number. So I like to say, like, rational and irrational numbers are close together. They're very close together. So anyway, so because rationals and irrationals are very close together, and inner billiards depends on whether your slope is rational or irrational, it's very unstable under small perturbation. On the other hand, by the way, if you pick your direction and you just move to the side a little bit, It's actually stable, does the same thing, basically. So, there you have it. All right, well, on to outer billiards. Yeah. Then you have to remember where you put all your things. Okay, so outer billiards is a particle bouncing around outside a polygon. So you might, like, how would you ever define that? Well, here's how it is. You have a billiard table, and then you have a point. So what you get to do is you get to pick a point outside, and you get to pick an orientation, either clockwise or counterclockwise. That's all you get to pick. So for this one on the left, I've picked clockwise, and for this one on the right, I've picked counterclockwise. And you start with your points, and then the way I like to think about it is you take a line and you sweep it down until it hits the polygon. And then you take the vector from your point to the point of tangency, or the point of hitting, and you double it to get the image point. And then you do the same thing. Yeah, does it make sense? Okay. So this was invented as a toy model for the solar system. Because the solar system, as you know, is like really complicated, so let's make a toy model where things are easier. And it was studied, so my PhD advisor studied it a lot. So that's why I got to know about it, because he was working on it a lot. Okay, so let's do the square table. So in all these situations, the square is the easiest, simplest thing. So I have my point here, and I'm going to pick counterclockwise because it's the math direction. So I have my line, I sweep it until it hits here, and I take this vector and I double it. Oops, not that button. Try again. Okay, try again. Okay, this button. Okay, I get that point. And then I take my thing and I sweep it until it hits. It's going to hit here, and I double it. And then I don't reflect off this point, because even though that's the next one, because when I sweep my line, it will hit this vertex. So I go up to there, and over to there. What do you think? Is it going to come back? Maybe. Nope. And let's keep going. Maybe it'll come back this time. Nope. Keeps going. Just keeps missing it. Oh, and now. Okay, now we go back to where we started. Okay, so this kind of looks like a mess. And you might think, like, how could there be any structure there at all? But check this out. I've made these points kind of big, and now I'm going to fill up the whole square that they're in. Boom. Okay. Okay, and so it actually turns out, so I started here, but it turns out that if I moved my point a little bit, all of these points would move, but sort of like symmetrically. Sort of like, yeah. So all of them would move in the same way. So it turns out that everything in the square does the same thing. And you could just move around in it. And so you can dissect the thing. So it turns out that each point is contained in a polygon of points that all do the same thing. In this case, they're squares. And so the images of these polygons under the map form what are called necklaces. As you can see why, right? They look like necklaces. So, keep pushing the same button. That is not the right button. Okay. So, here's a question. Under the square billiard table, using the square billiard table as your table, can a point escape? No, why not?
Because your initial point will always be contained in a square, so therefore you will always have some symmetry of the squares around the point as long as your slope is rational.
Certainly your point is contained in a square that all does the same thing. But in this case, the slope doesn't matter too much, because if I took my starting point and I moved it around, it wouldn't matter. It would still do the same thing. So in this case, your direction doesn't matter too much. But the idea is that if you start, taxi cab metric distance 3 from the middle, or whatever you want to call it, you start in this diamond, you always stay in this diamond. So you always stay about the same distance away. So if I started in this square, I'd always stay in this necklace. So you always stay about the same distance away. So you can't get, so no, you can't. So if you can see like the gray, the whatever, tan ones always stay in the tan, and the green always stay in the green, and so on. Okay, so people knew this about the square, and then people wondered, is there any shape of table where a point can escape? So when I came in to PhD, my advisor had been working on this very hard for a while. So Ebony, yeah, you had an idea.
I just wonder the significance of doubling. Like, can you escape if you quadruplet or triplet, or like, is that related to the radius of the necklace or something?
Oh, yeah, good point.
Yeah.
So what if you apply a scaling factor, right? You start with your vector, and then instead of copying the vector, you do like 1.1 times the vector. So I worked with a group of students who did it with contraction. So they scaled the vector by, I don't know, 0.9 or 0.8 or something, and saw what happened. And the behavior was different. It actually sort of had attracting fixed trajectories in that case. But we didn't, I think that if you scaled it up, I think it would escape. It would have to escape, yeah. Yeah.
The length of the vector would be growing without bound.
The length of the vector would be going up without bound, but you know, sometimes they're small. Sometimes you get an image point that's close. But yeah, I still think, I mean, if you said, do you think it's possible that given a certain table and given a certain scaling factor that you could possibly find something that didn't escape? I would say, yeah, you probably could. So that's what I'm trying to think of a counterexample. But I think in general, yeah, they would escape. Okay, good question. Great, future research problem. How about this? Do you think there's any shape of table where a point does escape? Yeah, I think it's not obvious at all. I mean, people kind of wanted to know because it was a toy model for the solar system, and we do want to know whether the Earth is going to spin out of orbit and, yeah, we're going to die. But it turns out that the answer is yes. And so my advisor came up with one solution, and a group of 2 other mathematicians came up with a different solution. So here are the 2 solutions. So my advisor, Rich Schwartz, came up with the Penrose kite, and Dolgopiat and Fayad came up with the half disk, and they both showed that you can have escaping trajectories. So Penrose kite, you might be familiar with the Penrose tiling. It's this tiling that I'm personally obsessed with, so I assume everyone knows about it, right? So it's this tiling of kites. Kite is this kind of shape, and a dart, which is like the Star Trek symbol. And they have markings on them so that if you fit them together, they only tile the plane non-periodically. So a periodic tiling is like the square tiling that's on the ceiling, and a non-periodic tiling is one that you really couldn't make wallpaper out of at all, because there's just no parts. You can't just make a stamp that repeats. And so this Penrose kite is very celebrated. It's based on the Pentagon, and it has these cool properties. Basically, it's a good rule of thumb, like if you want to find some weird behavior, try Penrose tilings. And so my advisor, being a smart guy, did that, and he found that for this Penrose kite, you can get escaping trajectories. And Dolgopiat and Fayad came up with the same thing for the half disk. So here's an example of outer billiards on a kite. This is not the Penrose kite. This is a well-behaved kite. This is a kite with like a rational, nice, rational parameter. But I put this picture up so you can see that in nice billiards, even outside of the square, you get necklaces. So, for instance, if you started a point here and you ran the outer billiard map on it, you would be reflected into another kite up there. And you go around, and if you started in one of these gray kites, you would stay in this big necklace of kites around the outside. And then the same thing, if you started in one of these rhombuses, you'd stay in you can kind of see the necklace of rhombuses even though it hasn't been identified by a color, and so on. Okay, but if you use a weird table, so here's a picture. I apologize for the low resolution of this picture, but there's a half disc here, and so we're doing outer billiards on the half disc. And so in these blobs, I think they're basically necklaces. So the blobs move together, like no big deal. But then in between you have this fractal dust. And weird things happen in the fractal dust. So if you started with a point in the middle here, in this fractal dust area, it would bounce around and probably escape to infinity. So my guess is that Dolgopiat and Fayad picked some special point in between here and were able to prove that it was a point. So life is weird when you're not on the square. Yeah. Okay. So with that, we conclude our study of outer billiards, and we can ask the same questions again. So, is there periodic behavior? Yeah, yes, on the square, at least. Well, probably yes on all the tables, really, at least on the square. On the square, and on the nice kite. I don't know about the Penrose kite. Is there dense behavior? Like, can you, if you start with a point, can its orbit be dense?
Didn't seem so.
It didn't seem so, so definitely not for the square. Not for the square, because then it only has a necklace worth of images. But you can try other shapes. So here's an idea. Suppose you use the circular table, or the disk table. Doesn't matter, circle or a disk, because we're not going inside. So suppose you start with your point, you do your billiard thing, you end up approximately here, then you do your billiard thing, and you end up approximately here, then you do your billiard thing. Maybe you can see that all of the image points would be the same distance away from the middle. So they'd all be on this big circle out here. And then the question might be, the image of this original point, can it densely, do you think it's gonna, will it be periodic? Or will it fill in irrationally this whole circle? Yeah, it could be either. Yeah, exactly. So if this angle theta is a rational multiple of pi, then it will, so theta, if theta is rational, it'll be periodic, and theta irrational, it'll be aperiodic, and thus dense in the circle. So that's kind of neat. Circle is usually a very simple case, and it is simple, but it can create this interesting behavior. So dense behavior, yes for the circle, and who knows for the Penrose kite or the half disk, I'm not really sure. How about escaping trajectories? Yes, so yes for the Penrose kite and the half disk, but no for the square. So the idea of filling in this chart is that there's like pretty rich behavior going on. Like there's yeses and nos and different cases for different things, even though these things are quite basic. Like basic by meaning like these are the type of things you'd ask for a dynamical system, and then you get all different answers. Okay, and how about stable under a small perturbation? How about for the square? It is stable, yeah, because if you move it within the square that it's in, its necklace, it does the same thing. Who knows for the others? Oh, this one would probably be no, yeah, because if you move its location a little bit, it would be different. So no for the circle. So that's interesting, because the square and the circle are quite simple, but you get different answers. All right. Are you ready for my question?
Can you run me this? What's the escaping trajectory mean again in the outer billiards case?
It means that if you start with a given point, its orbit, you start with a point within a finite distance of your table, its orbit would eventually escape any finite ball that you chose.
So it's non-periodic.
Yeah, definitely non-periodic, because anything that's periodic can be contained in some kind of a ball.
Yes.
But this one eventually, escaping means it eventually escapes any ball that you feel to choose to put on it.
Gotcha.
Yeah, okay. All right, so now we can talk about, well, I'm biased, but my favorite kind of billiards, which is tiling billiards. Okay. So in tiling billiards combines two of my great loves. So in college, I took this course on tilings. It was only offered once ever at the college, and I took it. And it was all about tilings, you know, the square tiling, hexagon tiling, but there's so much rich stuff in tilings. We were using this textbook that was about this thick, and every page was amazing. So I got really excited about tilings, and every time I travel, I see tilings. Every time I go into a bathroom, I look at the floor. I was really excited about the apartment I moved into in Swarthmore because it had my favorite tiling on the floor. Like, I'm really excited about tilings, but I never thought that it would really come into billiards, because you can't do billiards in a tiling. Billiards stays right in the tile. Like, what would you do? But here's a way that you can combine them. So if you have a tiling, like the square tiling, the one that you see on the ceiling in lots of places, here's this one here. So you shoot something, a trajectory, which you can think of as like a laser beam of light, and when it hits the edge, it reflects through in such a way that these two angles are equal. So angle of incidence equals angles of reflection, just like billiards, but in a different context. So you can ask, given your favorite tiling, what happens? And there are so many tilings, so many things to do. So this is motivated by Snell's law. So it may have been a while since you've seen Snell's law, but here's what it is. So Snell's law governs the refraction of a beam of light passing from one material to the other. So if you have something like air and water, and you are looking at, like a beam of light is going from one to the other, it changes its direction. And you can say exactly how it's going to happen. The materials come with something called an index of refraction, which are usually called like K1 and K2. And if you draw a perpendicular to the interface here, and you measure these angles, theta 1 and theta 2, it satisfies this relation. So that's Snell's law. Now, in the 1960s, some people thought, wait a second, what if we throw a negative sign into this equation? I wonder what would happen. So this is a standard material. What if you put in like a metamaterial, something with a negative index of refraction? Well, all that does is this angle, this one is going counterclockwise, now this one is going clockwise. So this angle is negative. So theta 2 is negative, so sine of a negative is negative, and it has a negative index of refraction, so this is negative. So it still satisfies Snell's law, it's just there's a negative sign on both sides. And so people thought, could this happen? And then in about the year 2000, physicists or physical scientists were able to create materials with a negative index of refraction, which they called metamaterials. So the question is like, now if I were holding a glass of water and looking at you, you'd have some idea of what it would look like. Like it would look weird. And if you see a window, you can't necessarily see that a window is there if you're looking directly through it, but if you look at it in an angle, sometimes you can tell. Here's a question. Suppose I was holding a chunk of metamaterial. What would it look like?
It looked like the wall over there, right?
It would like kind of like a mirror? What do you mean?
Would you, if the light bounced back to you, you would see like everywhere else the light then, wouldn't it?
Yeah, something like that. Yeah, that light would reflect through it in a strange way, and so you'd see things that were in other places. So, okay, so that's the motivation, and I'll say a bit more about that we want to understand what happens with metamaterials. And so the toy model that we'll work with is materials with equal and opposite indices of refraction. So that these angles are equal. The angle from the perpendicular are equal, and the angle from the material are equal. And so that's what tiling billiards is doing. It's saying, suppose you had, in this case, a two-colorable tiling, and you shot a laser beam through it in such a way that, you know, you have standard materials and metamaterials alternating. What would happen if you shot a laser beam through it? So this has some applications. This is not an applied math talk, but it does have some applications. The first one is to building an invisibility cloak. So you have probably read Harry Potter, and Harry Potter has an invisibility cloak. And when I think about an invisibility cloak, I think like you could see through someone, right? Like if you're wearing an invisibility cloak and I look at you, I will see you. And I think of that as like looking through you, but that's not possible. You cannot look through a person, no matter what. A person is made of like meat and bones and stuff. And so the only way to really have an invisibility cloak is to bend light around. So the idea of this picture is that like, this is the person, you don't want this person to be visible. And you bend light around in such a way that this light, okay, it bent around, but then it kept going. So this is like a straight line, and this is a straight line. So the viewer doesn't even know that the light is bending around this thing. And so these are arrays of metamaterials, and that's the idea, is to use that to build an invisibility shield. People are working on this. As you can imagine, the government would be interested in this. Like if you put your sniper here would be pretty helpful. And there are factories that are making metamaterials, so that's pretty neat. Also, you can make a perfect lens. So this one, so here's the thing. Let's see. Suppose you are trying to use a microscope to look at a very small object, right? You can use a microscope, you can use a scanning electron microscope. But here's a statement. It's hard to look at an object that is smaller than the wavelength of the light that you're using to see the object. Would you believe that? I think it seems plausible. And somehow metamaterials can get around that. So this is the dream, to make a perfect lens that could resolve in infinite detail. So that's the dream. I hope I have convinced you that we should wonder about this. Okay, so then the question is like, okay, what if I had a chunk of this stuff, what would it look like? Now, that's interesting, but it turns out that you can do paradoxical things with standard materials as well. So, for instance, we are going to do a magic trick. As you can see, this is not magic oil, this is brand new oil, right? So I'm going to open it fresh. Okay, you want to inspect this oil? You see that it's not magic oil? Yeah, taste it. And can you inspect this beaker? Check if it's a magic beaker or just a...
It looks like vegetable oil to me.
All right, you believe it. Great. Would you like to be my assistant? Okay, great. Come on up here with the beaker. Okay, so you can make the beaker disappear. All right. Maybe you stand behind the beaker so everyone can see. Great. Put the little beaker inside the big beaker. Great. And then pour the oil in until it totally covers the little beaker.
I'm shook.
Where's the beaker?
Did she fill the inside one also?
Yeah.
Yeah.
Both of them? You had to fill both.
Great. All right, you can pass it around. See, so can anyone say, like, so I'll start it here, but then pass it around. Anyone say what's going on here? Why did the little beaker disappear?
Snell's law is going to refract light one way, it'll hit the glass, back to the oil, back to the glass, back to the oil, and it'll appear straight through the entire lens.
Yeah, it goes straight through. It turns out it doesn't actually refract.
You can see
Does
the
it not?
bubbles color.
Yeah, because actually, Wesson vegetable oil and Pyrex have the same index of refraction. So that's what's going on. You can't see it because the light doesn't refract. So the only reason we could see the beaker, and you can see the beaker that you're passing around, you can see the top of it, because Pyrex and air have different indices of refraction, but Pyrex and oil don't. So that light isn't actually changing direction, which makes it impossible for you to see that thing. Pretty cool. So obviously, we should study tiling billiards. Okay, great. I'm glad you're convinced. Okay, so this is tiling billiards, and here we go. So suppose we start with our usual, which is, let's do the simplest one, the square. It's already on the ceiling. So in the square, perhaps you can convince yourself there are really, let's see, wait, I was gonna simulate this for you. Don't convince yourself, don't believe me, believe the applet. Okay, so this is an applet that a student, an undergraduate, wrote who was working with us. So here's what happens. You imagine that you are standing at the green point and you're shooting a laser toward the red point. And then it does tiling billiards. So you can shoot it in different directions, you can see what happens. What does it seem? Stable? Unstable? Stable. It's doing the same thing. I can move over here if you're not sure what's going on. But here's the thing. You shoot it further up, it does this thing, and then suddenly, it does that. Oh, you can see it. Okay. And then as you move it like this, it's pretty stable. It makes this rhombus thing for a while, and then it shoots off into the zigzag. So perhaps you can see why there's only really two things that can happen, the zigzag or the rhombus. The way I like to think about it is like, if you start here on an edge, you can go to the opposite edge, in which case you keep going to opposite edges and you get a zigzag. Or you can go to the adjacent edge, in which case you keep going to adjacent edges and you get a rhombus. So that's it. Those are the only options. So if we go back to our hero, so those are the only options, the zigzag or the rhombus. And so this is definitely a periodic path, a period 4, but this is kind of periodic as well. And so we give it a name, we call it drift periodic, because it's basically periodic, but with a drift. So periodic, but with a translation. Okay, so I'm going to talk about 2 different kinds of tilings that I've studied with different groups of people. Triangle tilings, again, this is what you're passing around on a piece of paper, and the trihexagonal tiling. So I'll tell you what are triangle tilings. So you take your favorite triangle, let's say it's this triangle, and you basically take a square grid and you put in parallel diagonals and then shear it until you get your favorite triangle. Or in other words, you could take the equilateral triangle grid and you could just shear it and stretch it until you get what you want. And so this is a canonical way of taking any triangle, your favorite triangle, and tiling the whole plane with that. So these are all congruent triangles, and we're going to study the whole space of them. The trihexagonal tiling, on the other hand, is just one tiling. This one you can have any triangle you want. This is only one tiling. It's the tiling where a regular hexagon and an equilateral triangle meet at every edge. Okay? Great. So those are what we'll do. So first we'll talk about triangle tilings. So I worked on this with Elijah Fromm, Suman Iyer, and Paul Baird-Smith, who were undergraduates at the small summer undergraduate research program at Williams College in summer 2016. So Elijah is now a PhD student in math at Yale, Suman is now a PhD student in math at Cornell, and Paul is now a PhD student in computer science at Texas. Where are they now? Now you know. So let's do a simulation again. So I will pick a triangle tiling. Would anyone like to give me some angles in degrees that you like?
90.5.
90.5? Is that what you said? 90.5? And another one?
Why do you like that one?
What?
Random.
17.
17. Do you want it to be random? I'll put a bunch of stuff on the end. Okay. So here's the Appalachian State University tiling. And again, we start at the green point and we shoot it towards the red point. And let's see what happens as we change our direction. What do you think? Stable? Unstable? Pretty stable. Let's see. So I'm shooting it to here, and one of them is probably approaching a corner. Which one? Probably the one at the top. So the one at the top is approaching a corner, and as soon as it hits the corner, it'll do something different. So what does it do? Oh! Ah! What's happening now? I don't know. Let's see.
Stair step.
Stair step. So it's like a periodic tiling, but in a different way, probably. But if I move it, it goes back to the same thing. Let's see. Get it back up there. Okay. This one, it looks like if we let it go a little further, it might close up. So let's kick up the iterations a little bit. Okay, so that one is periodic with a high period. That's pretty nice. Let's see, what if so I have this thing where I can just press W and the point moves up the screen. Not much is happening. Let's make it more exciting. I don't want you to fall asleep. Not on tiling billiards, you can fall asleep on something else. Okay. So if I run my red point down the screen, you can see maybe that it's changing a little bit, changing a little bit, changing a little bit, boom! And now it's doing some stuff, but it's pretty stable. Now I'm gonna run to the right. What happens if I run to the right? Not too much. What if I run up? Pretty stable. Oh, okay. So the idea here is that triangle tiling, trajectories on triangle tilings, pretty stable. So you know, I was confident that no matter what you said, it was gonna be stable, but it is pretty stable. We can also get smaller trajectories, like running around a single vertex. That, what am I doing wrong here? I'm not really sure. We're missing some of the page here. Oh well. Anyway, you can get small things that go around just a few vertices as well. Sorry about my technical difficulties. Okay. So, good. So, something we observed over and over again is that trajectories on triangle tilings are very stable. And also most of them are periodic. So even those ones that shot off, I think usually if we gave them enough iterations, they would actually come back and close up. So why? Like, this does not happen on the square. This does not happen on triangle billiard table. Like, why is this? Okay, now I need the thing back. We have the thing. Great. Thank you. Okay, so here's the proof. So here's a trajectory on a triangle tiling. This one is periodic. And I've taken that and printed it out on a piece of paper, which you've now all seen, I guess, because you've touched it. Great. And so here's a couple of observations. So first of all, if you look at an edge of the tiling and you look at the two pieces of trajectory that are refracting through that edge, if we fold along that edge, they line up on top of each other. Yeah? So if we were, by some miracle, able to fold along all the edges of the tiling at the same time, they would all lie on top of each other. And that's what I've done here. Yep. 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 Okay. So, you see? They all lie on a line. Pretty cool. Okay. So, the idea is this is a simplified picture of this, but you have all the triangles folded up, and then you have this one chord of into a circle, and then you have this one chord where all the trajectories are. So the idea is that we can turn trajectories on triangle tilings into just understanding how triangles move around a circle with an identified chord. Okay, so that's the first thing. Instead of studying trajectories on tilings, you can study triangles moving around inside a circle with a chord. Okay, so, so a triangle tiling can be folded so that all the triangles are inscribed in a circle, and then moving from one triangle to another amounts to rotating triangles around the circle, right? Just rotating around. So one thing you could notice is that right now, you can only see blue triangles, is that right? And I can only see red triangles. So we are just rotating, and all the blue triangles that you see are rotations of each other, because they all started out in the plane in the same orientation. We folded it, two folds is, so two reflections is a rotation. So that's how they're all rotations of each other. And then we can think of this as cutting up and reassembling an interval. So it turns out, and I'm going to brush this part under the rug, but if you want, we can talk about it. It turns out that if you try to keep track of how the triangles move, it just amounts to taking an interval, in this case just the circle, the interval from 0 to 2 pi, cutting it up and reassembling it in some way. And the way we do it, the way that you should do it is if the angles of your triangle are alpha, beta, and gamma, just 3 angles, you cut up 0 to 2 pi into 2 alpha, 2 beta, and 2 gamma. Okay? Then you take each interval, you flip it in place, and then you shift the whole thing over. So then so that's the idea. So this picture is supposed to indicate, the students made this picture, I think it's pretty suggestive. You take this interval and you go, whoosh, and that's the image. You see that? That's the idea. So suppose that you had a point right here. You go, whoosh, and your image is down here. Then you look up into the original, you say, okay, that's where you're supposed to go. Now where does my next iterate go? And then you say, okay, whoosh, we get to here. And you map it up to see, okay, now it's there. And then you whoosh, flip it over, and you get to here. And now we're sort of over the edge, so we get to there, but that's where we started. And so this thing is period 6, meaning it just goes around one vertex of the tiling. And so it turns out that if you do this kind of flipping, lots of things are periodic and very stable. So if you just wiggle this around a little bit, all the images wiggle around a little bit and it stays the same behavior. And within the whole red piece, basically. Well, that's not quite true, but within big chunks for sure. So that's why things are stable. Okay, so these things are super stable and this is why. And that's pretty cool. Okay, and the seventh thing we'll explore is the trihexagonal tiling. So this is work that I did with Pat Hooper, who is at City College of New York. So let's look at that tiling. Here we go. Okay, so we're going to do new hexagon triangle tiling. Okay, great. So here's the as you will recall, perhaps this is a regular hexagon and an equilateral triangle meeting along each edge. So let's see. So I'm going to take this point and I'm going to move it over here. And now I'm going to move it just a tiny bit. I'm going to give it just, let it walk up the screen in tiny little intervals. Are you ready? And if you want it to be even more impressive, we can kick up the number of iterations. What do you think? Stable? No. And also, by the way, it's looking kind of dense, isn't it? Yeah. We could, if we like this one, we could just leave it here and increase the number of iterations. So it's looking kind of dense. So this is something that we didn't observe at all in triangle tilings. Things were periodic, things were stable, and they were definitely not dense. So that's something that we proved actually. Oh, now I've got oil on my toy. We proved that a trajectory can only go through each triangle once, so it's definitely not dense. Okay, so this is what we thought was sort of bizarre about the triangle hexagon tiling. So our observations are that trajectories on this tiling are wildly unstable. You can change things a tiny bit and they change completely, and some of them appear to be dense. So here's a very accurate computer picture of a trajectory of 1,000 iterations with slope 1 on the tiling. So you can see it's filling in densely. But one of the things you might notice is that there appear to be these little white triangles that don't get hit. And indeed, that's what happens. So it fills in everything densely, generally, except for those little white triangles. So in this tiling as well, we have two types of periodic behavior, things that are legitimately periodic, like this thing here, period 6, or whatever. And then we have things that are drift periodic. They're periodic, but with a drift. Okay, and you might want to know, I want to shoot my ball in a direction that I'm going to get a periodic trajectory or a drift periodic trajectory. What should I do? Well, we proved this is how you get it. So you take the triangle lattice, the triangle grid, equilateral triangles, and now you imagine you're sitting here at the origin and you're looking out. Let's imagine that at every single triangle lattice point there's a tree, and so you cut down the trees that you can't see. So for instance, there's no tree here because it's blocked by this tree here. I can't see it from the origin. You know? So these are like the primitive directions. In some sense, they're like primitive directions. Okay. So you might wonder, so we showed that if you want to get periodic behavior, you should shoot your ball in one of these directions in this grid. So any of them. And then you might further wonder, like, how do I get periodic? How do I get drift periodic? Well, periodic happens, well, first of all, drift periodic happens at the points, the trees that are on like every third hexagon. So the third, the sixth, the ninth, and so on. And then the periodic directions are all the rest. So the ones that are equivalent to 1 or 2 mod 3. So I actually took these exact vectors, if you can see. I took them exactly from here, and I found their directions in this grid. It's kind of neat, so it actually works. So these are the periodic directions. So that could tell you why it's unlikely to have a periodic thing, because it's awfully hard to hit one of these directions. It's just as hard as it is to pick a rational number. And then our theorem is that trajectory in any direction not in that triangle grid is dense in the entire plane, except for these triangle centers. So I think that's kind of amazing. It means that suppose you had this big grant and you're able to purchase a bunch of metamaterial tiles. And since you're a reasonable person, you make the hexagons out of standard materials, and you make the triangles, which are smaller, out of metamaterials. And you just like make a huge lab bench out of it, and then you shoot a laser through it. The theorem says that with probability 1, if you just let it go and go, it'll fill in more and more and more until it looks like this. And if a laser is bright, if a laser is bright, then it ends up looking like this. So it fills up all of space except for these little dark triangle centers. So I think that's kind of amazing. That's what happens. That, like, this is generic behavior on the trihexagonal tiling. Yeah. Well, let's triumphantly record our last bit of observation. So we can answer this for the triangle, and we can answer this for the hexagon. So is there periodic behavior? Yes on both. Oops, yes, always. Yeah, we haven't yet found a tiling where there isn't periodic behavior. That would be an interesting question. Is there a tiling where there is no periodic behavior? How about dense behavior? Yes? Well, yes on the trihexagonal tiling. And the triangle tiling? No on triangle tilings. Because, as I mentioned to you very briefly, we did prove that a trajectory can only cross each triangle once, so no hope of denseness. How about escaping trajectories? Yeah, in fact, we can get them on both. I didn't talk about it too much for the triangle, so yes on both. Yes on both. And how about, is it stable under small perturbations? How about for the triangle tiling? Yes, it's so stable. How about for the hexagon, trihexagonal? No. So, I think that's kind of interesting that we started talking about inner billiards where periodic behavior was for rational directions and dense behavior was for irrational directions, and it turns out that the trihexagonal tiling is quite similar. And then we talked about outer billiards, where like you can move things around quite a bit and nothing really changes, at least on the square tiling. And that's the same kind of idea for the triangle tilings. So this is why tiling billiards is my favorite kind, because it's just so rich, and it incorporates a lot of the behaviors of other things. And also, there are so many more tilings left to study. Life is long, and it's going to be great. All right, thank you.
Any questions?
On your hexagon triangle billiards tiling, is the reason it can be dense and unstable because you have two different shapes of tiling, or does that have nothing to, is that other things going on?
Yeah, it would. We haven't really. So maybe the conjecture there's sort of an implied conjecture that you're saying, which is something like. What did you say? Unstable and dense behavior.
In other words, is the unique characteristics we get with the hexagon triangle tiling, is that because there's two different shapes in the tiling, or is there another reason for it?
Yeah, it's a great question. Maybe I'll leave that up. So we also have just octagon square tiling. So hopefully you can see it, even though, there you can see it, yeah, you can see it. So this is the tiling of octagons and squares. You sometimes see this. It's got octagons here and here. And so you might wonder if we can get cool dense behavior with this tiling. So far we have found nothing interesting enough even to think about this tiling. So it would be nice to know what the deal is. But this is like a counterexample to the conjecture because there's nothing interesting going on. So we do wonder what is the thing that makes triangle tiling so interesting and trihexagonal tiling, what makes things stable or unstable? So we'd like to look into that. One thing you can do is that there's a morphism that takes the equilateral triangle tiling, where nothing interesting happens, to the triangle hexagon tiling by sort of turning triangles into hexagons very slowly. So you, in the middle, you have triangles that look like this. They're kind of interpolating between equilateral triangles and hexagons. And so we'd like to know, like, if there's some point in this intermediary tiling where things change. But we don't know. If that's exactly the right question. What makes the different behaviors? We're not sure. Okay. You can work on it.
It seems like you can get a lot of really pretty pictures out of this. Have you found any neat, say, ways to make some more commonly known fractals or anything? Because a lot of this pattern is behavior is just self-similar by nature.
We have. Did you know that?
I did not. You
Okay,
have a cool construction of the Sierpinski triangle. I don't know what that was.
Yeah, okay.
Well, that,
We have,
that
actually.
circle with the, did you have fractal dust you said in the, with the house?
That was like Cantory stuff.
So, if you do the interval exchange thing, you can get a certain kind of, anyway, someone told us, why don't you try this certain thing, you might get fractals. And so, we did. And so maybe I can show you how this works. So one of our angles is 41 point, it has to be exactly right, basically, 0, 6, 6, 7, 9, 8, 8, 8, 5, 7, 7.
Oh, obvious.
I was just gonna ask about that,
Yeah.
yeah.
I don't know why no one suggested that one. 396, 203, 173. Okay, so this is a very special triangle. It's associated to, so what you do is, get your marker. So, you can have this equation, x plus x squared plus x cubed equals 1. And it has 3 solutions, but it has a real solution, x, which is approximately 0.54 in a lot of decimal places. And this is like a special self-similar number, basically. And so all the triangle angles are related to this number, to x. The 3 angles are related to x, x squared, and x cubed. So if you, and that's, then I put them in decimal form. So you get interesting things when your trajectory goes through the circumcenter. So let's see how big I can get it. I have to do circumcenter things. Yeah, that's pretty good. So it's going to approach what's called the rosy fractal. Yeah, that's bigger. And maybe you can see that these things are kind of self-similar. Yeah, there we go. Getting even better. Increase our iterations to 500. How big did we get? That's pretty big, not that big. Anything good in this area? So the key is really to put the thing at the circumcenter, and that's hard. I tried to get the student to change it so that it defaulted to the circumcenter, but he was like, I'm too busy. Deal with it, basically. So, sorry about trying to find the circumcenter live. It's in there somewhere. So the circumcenter is the intersection of the perpendicular bisectors of the edges. So, yeah, I'm not doing a great job here. But I can show you what you get. So, let me just show you. So this is the rosy fractal. This appeared in a paper of Hooper and Weiss. This is the original picture of the rosy fractal by Arnoux. This is a similar picture by McMullen. And so these are the ones that I was laboriously getting as I was clicking around. I think we got this, we started with this one, we got this one, and maybe we got this one. But as you shoot the thing closer and closer to the circumcenter, you can get bigger and bigger fractals. That's what I was trying for. And perhaps you can see that in horizontal rows, there's some similarities. They're like getting bigger and bigger, the same thing. And then the other thing is that you know about Fibonacci numbers. You take 2 of them, you add them, you get the 3rd one. Well, this is Fibonacci. So if you take 3 of them, you get the next one. So can you see how, if you have those 3 parts of that trajectory, you can pull them right out of these pictures? And it turns out the same one for the next one. This one, and this one add up to get that picture. So you have to have a very precise angles on your tiling, and you have to shoot it right through the circumcenter, but then you can get these fractal looking things, and we think that in the limit, they are space filling curves. Okay, well, that was a long answer, but cool, right?
Do you get fractal behavior when you look at for example, the necklace of the half circle,
Yeah.
right? I mean, so that's somehow like a Julia set in some way, right? It's really you're shading the set of initial conditions for which you get a bounded orbit or something like that.
Oh, yeah.
So,
Yeah, those would be necklaces.
So I guess my question, so you talked about the dust there,
Yeah.
right? When you get dust for Julia sets, that's often where you have a bounded non-periodic orbit. Is that right?
Oh, sort of like the thing on the circle that we did, it's bounded, outer values on the circle, it's bounded but non-periodic.
Yeah, but I guess so I'm asking so when you have you had the necklace for the half circle,
Yeah.
are those dust sort of pieces bounded non-periodic initial conditions, or is that
Yeah,
norm?
I don't know.
Okay.
Certainly some of the fractal dust is going to be have unbounded trajectories, because that's the theorem.
Right.
But you're probably right, probably a lot of it is bounded but non-periodic. That seems reasonable.
Any other questions? If not, let's thank our speakers.